Okay, we're going to talk about a very useful concept called dimension. Now, this is something that we've met before, but we're just going to formalize it. Remember, this is a similar situation to what we had with basis. Remember that we had a basis is a linearly independent spanning set. Okay, if you have a subspace and you have a linearly independent set that spans it, we call that a basis. Now, dimension also has to do with this same concept of linearly independent spanning sets. So dimension is equal to the number of vectors in the basis. Okay. Now, we've seen already that subspaces can have more than one basis. For instance, if I wanted a subspace of a basis of C2, I could choose the standard basis 1, 0, 0, 1. Now, another possible basis would be 1, 0, 1, 1. Those are both bases. And of course, the second basis is not orthogonal, but that's okay. It's still a basis. So these are two different bases of C2. So, however, note that they both have two vectors. The number of vectors in the basis is characteristic of the subspace. Okay, and that's what's called the dimension. Now, we haven't proved that every basis of a certain subspace has the same number of vectors, but that's what we're going to prove. And that's why dimension is so important, because it's characteristic of the subspace. And this is an idea that's very familiar from daily life. We talk about we live in a three-dimensional world, or a plane is a two-dimensional surface. So we already have that intuitive idea that dimension is characteristic of the space and not of the particular basis that we use to coordinatize that space. All right, so let's launch in with these definitions and we'll see how this plays out. All right, so a definition, mathematical definition of dimension is, we suppose V is a vector space, and suppose we have a basis of t vectors. So again, these are linearly independent and they span V. Then the dimension of V is defined as t. It's the number of vectors in the basis. Okay? If the vector space has no finite basis, then we say V has infinite dimension. Now, there are vector spaces that have infinite dimension. We talked about one earlier. The vector space of functions is infinite dimensional. The vector space of infinite sequences is infinite dimensional. And most of the vector spaces that we'll be dealing with have finite dimension. Okay? Right. Now, I mentioned that the number of vectors in a basis is independent of that basis, and that's what we're working towards. We need to prove that. That's not something that we can just assume. So we're going to take several steps in that direction, and this is the first step. So this is called spanning sets and linear dependence. So suppose we have a finite set of vectors which spans the vector space V. Okay, a finite set of t vectors that spans the vector space V. All right, we're not assuming that this is linearly independent or dependent. We're just saying that it does span V. Then any set of t plus 1 or more vectors from V is linearly independent. Okay, so if I have t vectors that span, if I have even one more, if I choose any set of t plus 1 vectors from V, then I know automatically that that's linearly dependent. Now, we've seen similar situations before. For instance, when we had a matrix that was not square, and you had n rows and m columns, if we knew that m was greater than n, automatically we knew that there were free variables. Okay, so this is the same sort of conclusion, that if the number of vectors is bigger than a certain threshold, then we get a linear dependence. Okay, so and you're going to see that the proof actually is related to this. So let's see. So let's suppose. Let's go through this theorem. Suppose we have a set of m vectors where m is bigger than t. Okay? And we want to construct a non-trivial relation of linear dependence on R. Okay? Now, since these m vectors are contained in V. That means they're spanned by these vectors V. So I can write every vector U as a linear combination of the vectors V. All right? So notice here I have M equations and I have T variables. Okay? Okay. We've got M equations and T variables. All right, now, the proof makes a step here that's not motivated, but later on you'll see why it does this. So we have M equations and T variables, and notice that M is bigger than T. Okay. Now, look at the columns here. The column goes A11 up to A1M, A21 up to A2M, A31 up to A3M. I'm going to turn these into rows and create the homogeneous system using these columns as my coefficients. Okay, so I have a homogeneous system. And again, in this case, I have T equations and M unknowns, and M is greater than T. Okay. All right, now what we have here is a homogeneous system with more variables than equations. So there are infinitely many solutions. We know there are free variables, and we can find infinitely many solutions. Okay, so let's suppose the solution to this system, we'll call that C1 through Cm. Okay? And let's see what we can do with these constants C1 through Cm. Suppose I form a linear relation using these constants with these vectors u. Now remember, these are the vectors u that I want to show are linearly dependent. Okay? Now the other thing I know is that each u can be expressed as a linear combination of v's. Okay, so u1 can be expressed as this linear combination, u2 can be expressed as this linear combination, and so on. Okay? Now we're going to do something that we've done similarly before. Look at all the terms that have v1 in them and group them together. And then look at all the terms that have v2 in them and group them together, and so on, all the way up to the end. And what you get when you do that is exactly this system of equations here. These are all the constant terms that multiply the v1 all grouped together in one place. All the constant terms that multiply v2 grouped together in one place. Now notice something. C was the solution, the homogeneous system with matrix A11 up to A1M. Okay? So in fact, this sum here, since C is the homogeneous solution, this is 0. This is 0. This is 0. All of these are 0. Okay. So what do we have here? We have a linear dependence relation for the vectors u. Okay. Not all the c's can be 0 because we know we have a non-trivial solution to this homogeneous system. Okay. So we've shown that if we have a spanning set with t vectors, then any set with more than t vectors will be linearly dependent. Okay. I'm going to skip this alternate proof, which is more uses more coordinates, but you can look at that at your leisure. Okay. Just want to point out here this comment that we did prove something very similar before for column vectors. This theorem. So if that theorem looks familiar, then you were right. That we've seen it before. This theorem for column vectors says the very same thing, that if I have n vectors in Cm and the number of vectors is greater than the dimension of the Cm, then S is linearly dependent set. So I hope you can see that this is a special case of what we've just proved. Okay. All right, so let's look at an example. Let's consider the vector space P4. And we're going to take a set of polynomials here. We've seen this set of polynomials before. Here's the first one. Sorry, it didn't take. Okay. Here's 1, 2, 3, 4 polynomials in P4. Okay. Now, by the way, we know that there's a basis of 5 polynomials in P4, 1x, x squared, x cubed, and x to the 4th. So this has only 4 vectors in it. We showed that this is a spanning set for all polynomials that have 2 as a root. Okay. So let's apply this theorem with t equal 4. So any 5 vectors must be, if you take any 5 vectors from this set that has 2 as a root, then they will be linearly dependent. Okay, so you can check that 2 is a root of every one of these polynomials. Okay, and by the theorem we've just shown, we can show that we know automatically that these must be linearly dependent. We don't have to do any calculations. We don't have to do any verification. Okay. So I told you that this theorem that we just showed is a stepping stone to the important theorem, which is that bases have identical sizes. I want to show that every basis of a vector space or any basis of a subspace has the same dimension. Two different bases of the same space have the same dimension. Okay, so let's suppose V is a vector space with finite basis B and second basis C, then B and C have the same size. Okay, and what we're going to do is we're going to cleverly use what we had just now. Basically, we're going to say, suppose C had more than B and get a contradiction, and then we'll suppose B has more vectors than C and get a contradiction. Really, it's the same proof running backwards and forwards. Okay, so let's suppose that B and C don't have the same size, and that C has more vectors than B. Okay, now we know that B is a spanning set for V, and that means that C must be linearly dependent. But we said that C was a basis, so that's a contradiction. So C must also be, so it's not possible to have the basis C have more vectors than basis B. Now, on the other hand, we can work this the other way. Suppose B has more vectors than C. C is a spanning set, and that means that B must be linearly dependent. So that means that B can't be a basis. So you can't have one basis have more vectors than another basis. Okay, so they must be equal. Okay, so that's a very good thing. All right, so I'll stop here and we'll go on with the next video.